Good afternoon, everyone. That's better. I'm Sean Hargreaves, and I'm here to talk about making awesome, cool-looking, fast-running stuff on Windows Phone 7 series. So whenever you talk about performance, whether for games or Silverlight or anything else, it has to start with hardware. And in the design of the hardware for this phone, we balanced a couple of sets of different requirements. The overarching goal for this phone was to do the right thing for the end user. And when we talk to end users about what they want to see in phone hardware, we hear they want choices. They want options of different colors, different sizes. But the other thing they tell us they want is great apps and great games. To get those apps and games, we need you guys to go and make them. So we went out and spoke to a bunch of guys like you about what you wanted to see from hardware. And the thing we hear again and again from developers is we don't want choices at all. Choices are bad. Choices fragment the ecosystem, and they make it hard to make products compatible across different phones. So the thing we've done with this phone is to create a consistent set of hardware. So you have the same CPU, the same GPU capabilities, the same amount of memory across any different phone. The one thing that's not entirely the same is the screen resolution. There are two. At launch, we're going to have an 800 by 480 resolution. And then at a later time, we're going to be adding a 480 by 320 resolution. And the good thing here is that's just two resolutions. It's not thousands or tens of thousands. And the other good thing is we have a cunning plan using a hardware scaler to make it very easy for apps to support both of these resolutions at the same time. I'll talk more about that later. So of all the hardware in this phone, the two things that matter the most from a performance point of view are the CPU and the GPU. This talk is organized exactly along that split. For the first half, I'm going to talk about CPU performance. And then, the second half, I'm going to show you some graphics and talk about the GPU side of things. The most significant factor of the CPU performance on this phone is that it's a managed code programming environment. All your code is written in C#, and it runs in the .NET framework. This is kind of a new thing, especially for a game programming platform. Most games today are written in C++. Not all. XNA Framework has been out for 3 years now, and there are quite a lot of Xbox Live arcade games that are written using C#. But this is really the first time a major platform has been C# only. And when we tell developers this, they say, OK, we like the fact that C# is productive. We like the fact that it's a great development environment. But we're kind of nervous about the performance aspects of what that's going to imply. The thing that's interesting for me about this slide, you could read this as a contrast of C++ versus C# from a performance perspective. But this could also be a debate that was going on when I got my very first job in the game industry. Back in 1996, straight out of college, I was hired onto a team that was making a Nintendo 64 game, which was written entirely in C. The only other programmer on that project, the lead programmer, had come from a project that was previously for the Super Nintendo and was written entirely in assembler. And he had some concerns about switching to C. He was saying, I don't know, it's productive for sure, but man, I just don't have the control over what's going on. I can't really do self-modifying code in C. And I don't know if I'm going to get the performance I need without that. The strange thing about this debate is it only goes in one direction. Looking back from where we are now, the idea that you would write game logic in self-modifying assembler code is kind of scary. In my time in the game industry, I got to see this whole debate a second time when the industry moved from C to C++. That was kind of a gradual transition because C++ is fairly backward compatible. So it went in stages. I like to use this piece of code as an interview question for C++ programming candidates. And the interesting thing is that there are so many different ways people react to this code depending on what their background is and what their programming experience has been. If I wrote this code in my day job as a C++ game programmer in 2000, I probably would have got fired on the spot. My boss would have said, you are using dynamic cast, there's the door, get out. Right back then, we said we used C++, but we wrote C code and ran it through the C++ compiler. We had coding standards that said things like, you can use those 2/ comments, those are cool. Don't use classes, don't use virtual methods, that stuff's too slow for games. Around about 2003, 2004, game programmers had gone object happy. There were objects everywhere, crazy inheritance hierarchies, everything was virtual. But this coding standards book said, do not use templates, templates are evil, they're too slow for games. STL is just, no, don't go there. By the time I joined Microsoft in 2006, game programmers were using STL a lot. We were writing code very much like this. And the reason we could do that is because the game industry has learned how to make C++ code efficient. And it turns out simplistic rules like don't use dynamic cast, that's not really it. Because often you take that rule and you go and write your own replacement of that same functionality that's probably slower than what the compiler came with built in. And simplistic rules like don't use STL, well, be smart. Use it when it makes sense. Don't use it wrongly. So the great thing I get from asking people how this code's going to perform, a really good game programming candidate will look at that and say, hey, this could be all right. I want to know what type is that entities collection. What is its iterator actually going to do? When you call new collision info, what's the allocator for that class? Is that a custom allocator that's going to be super friendly, or is it just the standard C++ allocator that's going to fragment the heap if I run this code too many times? Game programmers have gotten very good over the years at understanding C++ code at that kind of level of detail. .NET we're just starting to learn about. .NET's been around for a long time. It's been used very successfully for enterprise applications, for web development, for server, user interface programming. We're just starting with games. And my goal with this talk is to show you some of the things you need to be aware of, some of the equivalents of how do you make C++ code go fast, but for .NET. Before I dive into some performance details, let's just talk about why are we doing this in the first place. Performance talks can come across kind of negative because I spend all the time talking about don't do this, don't do that, this risks being slow. It's just kind of depressing. So before I start with all the slow stuff, let's talk about some stuff that's not slow and that's just good, and why we chose this platform in the first place. C# is a great language, and probably the best thing about it is the type safety. Coming from a native code background, I'm amazed how I still make mistakes in C#. I make probably as many mistakes as in any other language, but they're very shallow. Because of type safety, when I do a silly logic error, I get an exception, probably on the same line that I made the mistake, maybe the line after. In C++, that same mistake could corrupt memory, my program runs for another 5 minutes, and then it crashes deep in the sound subsystem. And I'm left scratching my head trying to figure out why. We hear this all the time from game developers using XNA. Sure, they make mistakes, but their testing phase is way shorter than they're used to from C++ projects, because they get a call stack, and they just go look at the line of code it points to, and they're like, yep, there's where I made the mistake. Reflection is an incredible ability coming from a native code background. It lets you make code that's self-aware. So if you're interested in creating Skynet and taking over the world, this is how you do it. For game development, this is superb for replacing things like custom level editors, where you can write code that just scans over all the objects in your game, pulls out the properties in them, and gives your designer user interfaces for doing things like I'm going to tweak this value and make this thing run faster or be brighter colored. The initializer syntax in C# is tremendously useful for things that in other languages you would have to use scripting or external configuration files for. We all have this kind of mantra, data-driven good, hard-coded bad. But hard coding really depends on what is it you're writing. Often in a game, you'll find the things that you hard code that you want to data drive are still shipped with your application. All the rules for how fast does my enemy run, how fast can he fire his bullets. It's really a question of, do you have a nice syntax for gathering that data together in one place? And in C#, you can use object initializers to do that just directly in your project, and you often find you don't need to do things like parsing external XML. Compile time is amazing. Working on the XNA framework back in Redmond, in my day job, I create probably equal amounts of C# and C++ code. The C++ code for the XNA framework takes about 25 minutes for a clean from-scratch rebuild. The C# code, less than 1 minute. That's huge. The tooling's awesome. And if you're a native developer who's looking at Windows Phone for the first time and thinking, hey, I know C++, I don't know C#, it's very easy to learn. The two languages are similar enough that you're not going to be confused. When you look at performance, it's important to understand that the XNA framework runs on 3 different platforms. The behavior is consistent across them all, but performance kind of breaks encapsulation in a lot of ways. So it's important to be aware that they're not the same runtimes, and some performance characteristics are different. On Windows, .NET code performance is really very impressive. It's very close to native code. The garbage collector is very sophisticated and generational. This URL here points to a little competition that was run between a couple of Microsoft bloggers. Raymond Chen wrote a simple C++ app that loaded in a big file and sorted it and computed some data. Rico ported that same thing to C#, and then they competed to optimize that code and see who could make it run the fastest. The interesting thing is that Raymond spent about 3-4 weeks working on this and went through about 10 versions. By the end, he'd replaced his string class, he'd replaced the memory allocator, he'd written a custom dictionary type, he'd replaced the system file I/O with an entirely custom set of calls, and he'd made it like 500 times faster. Recode's very first version, where he did the naive, just take the C++ code, translate it to C#, ran about as fast as the fourth iteration of the C++ code, just because .NET had a good string class and a good dictionary built in. When Raymond overtook and got faster, Rico went in and did a couple of very simple algorithmic optimizations and got to about the 8th version of the C++ code in performance. In the end, C++ did win, mostly because of startup times. It ended up, they both got the actual computation so fast that it was just dominated by loading the CLR, and there wasn't much you can do about that. But it was really interesting to me that they were very close performance-wise, and the C# version got there in 5 minutes, whereas the C++ one took weeks. If you've used the XNA framework on Xbox 360, not so similar. There's much bigger delta between managed and native code performance. There's a couple of reasons for this. On Xbox, we use the Compact framework, which has a simpler garbage collector than on Windows. But the biggest reason is Xbox is a special-purpose machine. It's not a general-purpose computing device. It has a very unforgiving CPU architecture that doesn't like branches. It likes very deep pipelines. .NET tends to make quite branchy code, and it's just not a good fit, not the right kind of code to run on that CPU for awesome performance. The awesome math performance in the Xbox 360 comes from custom VMX instructions, and .NET just doesn't know how to generate those, so a lot of the CPU is just sitting idle. And also, the 360 has a unique security architecture. It's designed to prevent piracy and to prevent cheating in online games. And one of the main things this does is it prevents changing code, because if you could change code, you could cheat. But .NET and jittered languages are all about generating code. So the .NET runtime basically does exactly what the hardware is trying to make impossible. And we have to jump through some fairly crazy hoops to make .NET code run at all that have a performance penalty. So on Xbox, .NET code's great for some things. It's great for productive, rapid iteration, for quickly producing a game. But if you need maxed out performance to get every inch of power out of the metal, C++ can be a better choice for some games. On the phone, you'll see performance kind of in between the Windows and Xbox extremes. The phone uses the Compact framework, so garbage collection is not generational. I'll be talking much more about this in a few moments. But the CPU is a much better fit for .NET code than the Xbox. It's an ARM CPU, which just by its nature is more forgiving towards the kind of things that jittered code tends to do. And also, .NET's run on ARM for much longer than it's run on PowerPC, so our jitter is just more mature, and it does a better job. Starting with the absolute fundamentals, there's a lot of different ways you can call code in .NET. A direct call to a method is obviously the fastest. Virtual method, a little bit slower. Interface, slightly slower than a virtual method. Calling through a delegate or an event. Events are just syntactic sugar for delegates. That's slower again. And now you have to imagine there was a much bigger gap than between all of those four. Reflection is by far the slowest way you can call things. I'm not saying don't use it. Try and do it like at load time. Don't do it thousands of times every frame while a game's running. Something that's very important for people moving from native code to managed code is to understand the object model of what is memory and how do you refer to pieces of it. In C++, memory and objects are independent. So you can have a class or a struct that's just some combination of bits. And then you can get some memory by calling new or allocating it on the stack, or just calling whatever random API you like to get memory from a custom allocator. And you can use placement new to say, this memory is going to contain this object. And then you get to pick how you refer to that piece of memory. You can use a pointer or a reference or a direct copy of the value. .NET's not quite like that. In .NET, there are really two categories of objects. There are value types and reference types. And each of these comes with its own associated semantics for what memory it lives in and how that memory is referenced. Value types covers all the built-in primitives like integers, booleans, any structures that you create, and also built-in structures like the vector3 and matrix math classes. Reference types are anything that's a class, anything that's an array or a string or a boxed value type. So what's the difference between a value type and a reference type? If you look on the internet, you'll see a lot of articles that tell you one lives on the stack, the other lives on the heap. That's nearly true. From a performance point of view, it's just not quite true enough that it can be really misleading. The real difference is that a value type is just a thing without any kind of wrapper around it. So it lives wherever it's declared. If you declare a local variable of a value type, local variables go on the heap, so the value type is directly on the heap. A reference type consists of two chunks. There's a large piece of memory allocated on the heap, which controls the data for the object. And then there's a smaller pointer to that memory, which is basically a value type and has the same semantics as a value type. And the two always go together, so there's the object and the reference to the object. So if you imagine something like an array of integers, the array is a reference type, so it goes on the heap. The integers are value types, but they don't go on the stack. They go inside the array, which is on the heap. C++ guys tend to get tripped up by this because they think they know what's going on with pointers, and they see class and they see struct as two keywords, and they don't quite mean the same thing. When you come to choose between the two for custom types you're creating, general advice is you should start with classes if you're in doubt. They're less likely to have surprising characteristics. Use structure if your object is small and if it doesn't live very long. If you have high-frequency code that you really care about performance of, consider passing structures by reference instead of by value. This example shows the matrix multiply function from the XNA framework. If I pass two matrices to it and then return a third matrix, that's copying 192 bytes of data. The XNA framework math library has by reference overloads of all of the math operators, so you can speed that up by using the second version I show there with the ref keyword. That makes your code a little more verbose, a little harder to maintain. Don't do it everywhere. Just be smart and do it in the tight loops where you really care about this stuff. Garbage collection is something you need to be aware of in .NET. This is not a problem for every game. There's a myth out there that .NET garbage collection is just something you constantly have to be thinking about. That's actually not true. We find that many games just work fine. You just write them, you ship them, you're done. Some games will run into problems with the garbage collector. And when that happens, people often say, hey, can I turn it off? It's causing me trouble. Just make it go away. Well, no, you can't. The reason for that is very simple, that type safety requires automatic memory management. This wasn't obvious to me the first time somebody explained this, but it actually makes a lot of sense. If you did memory management manually, then you have the chance to get that wrong. And if you get it wrong, as soon as you make one silly little mistake, you're back into the C world of dangling pointers and corrupted heaps, and you don't have that simple debugging. So we need garbage collection to make sure that objects always point to what they think they do. They're either null or they're valid. There's no corrupted in-between states. And garbage collection's not all a bad thing from a performance perspective. It actually has some really cool advantages. If you compare it with the C++ manual style, in C++, allocations start out fairly fast. But the more your program runs, the more fragmented the heap gets and the slower everything gets. The way .NET allocations work, you have a chunk of memory that's in use, and then you have another chunk that's free. So allocating memory is always just grab the pointer to the base of the free block, increment it by the size of the object, done. It's like 3 CPU instructions. Very, very fast. The problem is that you allocate, and you run out of space. And then at that point, we have to do a garbage collection, which is where that can take some time. Freeing memory in .NET is actually free. You don't do anything. It's just stop using it, done. The nice thing about the .NET strategy is because we always have this block of memory that's contiguous and then this other block that's free, if you allocate 5 objects in a row, you're guaranteed that they will be next to each other in memory. C++ doesn't give you that guarantee unless you go and write a custom memory allocator. That's great for cache coherency, because we tend to have in programs, we have structures where we're going to loop over a bunch of objects, and whenever we process the first one, we're immediately going to process the second one after it. It's great for performance if, when we touch the memory for that first object, the second guy gets pulled into the cache too, because they live next to each other. C++ game programmers go to a lot of trouble to make that happen, customizing the memory manager. In .NET, it just happens for free. Just write simple, obvious code, and it will be cache coherent. The way garbage collection works on the phone and on Xbox 360 is the same. The garbage collector triggers every time you allocate 1 megabyte of memory. It maintains a counter of how much you've allocated, and when that passes a megabyte, this process kicks in. It starts with all the references to objects that are on the stack or in static global variables, and it follows those links to find what other objects they point to. And it recurses and follows every link that's inside an object to find another object, and it goes on doing this until it runs out of links to follow. At that point, it knows that it's seen every piece of memory that could possibly be reached by your program. So anything it didn't see, you can't possibly reach, therefore you can't possibly still be using it, so we can throw it away. And at that point, it's got some chunk of memory that's used, and there's going to be holes where objects in this memory were no longer used. So it compacts the heap, sliding down the memory from above the hole until all the holes are filled, and you're left with just one contiguous block of memory that's in use. So if this process takes too long or happens too often, you're going to see poor performance. Your game will typically hitch. It'll run smoothly for a while, and then go chunk, garbage collect, and then carry on running. There's two ways you can deal with that, two totally opposite strategies. One way is to say, hey, this thing takes too long, so let's not do it. That's actually very straightforward to understand how to achieve. The garbage collector runs every time you've allocated 1 megabyte of memory. Don't allocate a megabyte of memory, and it won't run. It's as simple as that. So do your allocations on startup while you're loading content, while your game is initializing. Allocate everything that you're going to need. And then you're done, and you can play, and it can be smooth, and you never touch the allocator. The other way is to say, I'm going to let it run. I'm going to let it run as often as it wants to run. Every frame is fine. I'm just going to make it run really, really quickly. If it takes 1 millisecond, 2 milliseconds, not a problem. My game's still going to stay smooth. The important thing to understand here, how long the garbage collector takes to run is directly proportional to how many references to objects are on your heap, because it just follows them all. More references, more things to follow, it's going to take longer. So don't put much stuff on your heap. That sounds kind of silly because you're thinking, I want to make a complicated app. How can I not have things on my heap? But what we tend to find when we look at memory usage patterns, particularly in games, but really in any kind of app, there's usually one kind of data that dominates the memory profile. A game might have a player object, and they have an enemy. They have 100 enemies on screen. Well, 100 is nothing for the garbage collector. To be talking the kind of number of objects that are really going to slow this down, you need to be talking tens of thousands. And then there's not many things that you have 10,000 of. That might be particles in a particle system. It might be triangles in a collision tree, if you have a tree of subdivided BSP hierarchy. And every single triangle is a separate object. And every single triangle has a reference to the one next to it and the other one, and to a bounding box, and a reference to its parent in case you want to walk back up. Suddenly, you're talking a lot of references. The great thing is if you can identify 99% of my heap is this one object here, just go fix that guy to not be references. Make it a value type. Put it in an array. Instead of storing a reference to the parent object, store the index of the parent object inside that array. If it's all value types, the garbage collector can just look and say, this array is 20 megabytes in size, and it's all value types, and I'm not even going to bother looking inside it. That's very fast. There's a method in .NET called gc.collect, which tells the garbage collector, right now, run. Don't wait until you hit that megabyte threshold. Don't call this every frame. We sometimes see people doing that because they think, I'm going to keep on top of this. I'm not going to let the garbage build up. The problem with doing that is that it takes just as long to run if you run it every frame as if you let it go 10 frames. So you're just paying that price more often than you have to. The one time when it can make sense to call this is if you have a situation where your program is loading some stuff, you're loading, allocating. It'll probably garbage collect a few times while it's loading. But depending on where the phase of this ends up when it finishes loading, you can get into a situation where you've allocated 900 kilobytes, and then gameplay begins. And if you've optimized your game code to the point where it hardly allocates everything, you haven't quite got it down to 0, but very nearly 0. So gameplay begins, but you're already at 900K. So even that very slow allocation rate can quickly push you past the megabyte threshold, and you get a hiccup. If you call gc.collect right at the end of loading, immediately before you start gameplay, that resets the clock back down to 0. So now you're starting from nothing. And if your allocation rate is low enough, you may say, hey, my game is going to hitch after 12 minutes, but I happen to know that my level takes 3 minutes to complete, so I don't even care, and you're done. The other time you can use this is things like if the player pauses. Call gc.collect while it's paused. They won't care that there's a slight performance hitch, and that will, again, give you that headroom back. Depending on your game design, you can often hook this to gameplay events. Like if you have a situation where a boss slides onto the screen and pops a little text box for the player to read, that's a pause in the interactivity. And whenever you get one of those pauses when real time is temporarily suspended, that's a great time to force a collection and reset the clock. If you go down the route of optimizing garbage collection by not letting it allocate memory, here are some common culprits that tend to surprise people and often are the reason this will happen. Boxing can be surprising. This is when your code treats a value type as if it was a reference type, so it gets moved onto the heap and an allocation happens. Careful with string formatting. Strings are not mutable in .NET, so anytime you do formatting, you create a new string. You can often avoid that by using the string builder class instead of strings. And all the XNA framework text functions have overloads that you can draw directly from a string builder, so you never need to create string objects at all. If you want to find out how much is my game allocating, how often is the garbage collector running, there's a couple of things you can do. You can use the weak reference class. The way this works is you set up some code that allocates an object and immediately throws it away, stop using it, and set up a weak reference to point to the thing that you just threw away. So the next time the garbage collector runs, that reference will go dead, and you can check it to say, OK, garbage collector must have just run. So you can use that to build a timer that you can display on the screen to show how often the collector is running. That URL shows you some code for doing that. Another great tool is the CLR profiler on Windows. This doesn't run on the phone directly, but using XNA, it's very easy to make a Windows version of the same code that you want to run on the phone. So you can use CLR profiler on Windows, and that will show you exactly where your code is allocating, how much, what types, which line of code is doing the allocations. It's a really good tool. The final tool I want to point you to, everyone who cares about performance and is using .NET needs to have this thing installed. It's awesome. .NET Reflector lets you turn compiled assemblies back into source code. So you can look at the C# code that they were created from, or you can even go right down to the IL level and look at the instruction tokens. And this is important for understanding what the compiler does. C# is a high-level language. It has some great features. It's very productive. Some of those features aren't totally obvious how they map from high-level source code to what's actually going to run on the CPU. And to get great perf, we need to understand that. I use .NET Reflector all the time when I have questions. Like, I'm not sure, is this going to be fast? Just go disassemble it and have a look at the code and see for yourself. One such example is the for each statement. We use for each loops all the time. It's a very common programming construct. You'll see a few performance articles that say, hey, be careful, don't use it, it creates garbage. It's kind of more complex than that. For each is syntactic sugar. The compiler turns it into an operation that calls getEnumerator on the collection, stores the enumerator object, and then keeps calling the moveNext method on that enumerator. So from a performance point of view, the thing we need to understand is what type is that enumerator? If it's a value type, it just goes on the stack. It's usually very small. And the moveNext calls are going to be very fast, and no garbage is created. If it's an interface or a reference type, then that getEnumerator method is going to have to allocate new memory, and there's going to be much higher overhead to this loop. So look in .NET Reflector for the type you're interested in and see what type is its enumerator. Arrays, lists, and most of the collections built into XNA have value type enumerators, so they're totally fast to use for each over. Some collection types, like dictionary, the enumerator is a reference type or an interface. This is another great example of C# compiler magic. Enumerator methods are an awesome thing for game programming because they basically let us write linear code for things that are not linear, and the compiler will unwind this and turn it into a state machine. This comes up all the time in game programming because we want to write things like, I'm the AI or the scripting logic for an enemy player. I want to start here. I want to walk forward 6 feet. I want to pause, then look around, see if there's an enemy. If there's an enemy, I'm going to load my weapon. And then when it's finished loading, I'm going to fire it. But you can't just write that code in a linear fashion because while this is going on, you need to be updating other enemies and running around the game world and drawing graphics. Some games try and use threads for this, but threads are kind of heavyweight. And if you fire up a separate thread for every single entity in your game, well, not always a great choice. Iterator methods are awesome because we can write this code that looks very straightforward and just goes through, do this, then this, then this. And whenever we want to suspend control for a while, we use the yield return keyword. What the compiler does with this code, it turns it into that. It creates a state machine. It creates a private internal class that stores all the information necessary for the execution of this function. And it generates a moveNext method, which is basically a switch statement that looks up, where had I got to in the running of this code, and carries on from that point. So you can call this once, and it will run just up to the first yield operation. Then you call it again, and it will pick up where it got to and resume from there and run to the next. It's tremendously useful, but also tremendously useful to use .NET Reflector if you're writing this kind of code. Because if you think that what's actually running on the CPU is the nice, neat linear code that you wrote in your editor, well, no, that's what's actually running. And it's useful to understand that if you don't want to get surprised. So that's a quick overview of some CPU topics. Now let's look at the graphics side of things. All Windows Phone 7 series devices have a GPU. It's a pretty powerful graphics card, so we support full hardware-accelerated 3D rendering. In XNA Game Studio 4.0, we have a palette of 5 built-in effects, which have a number of different options to configure them. So you should think of this as like your painter's palette for creating great-looking graphics in games. These are the 5 guys you're going to use to draw everything to the screen. And I'm going to go through them all and show you what they can do and some of the different options you get to configure them. We also have hardware-accelerated 2D sprite drawing via the sprite batch class that can do scaling, alpha blending, rotating, all the kind of obvious 2D stuff. But I'm going to concentrate on the 3D shaders here. The first one is Basic Effect. This guy has been around in Game Studio ever since our first release, version 1. The other 4 of these effects are new in Game Studio 4. The Basic Effect does lighting, it does texturing, this is the kind of standard default for drawing solid 3D objects. It supports anywhere from 0 to 3 lights. It uses the standard Blin-Phong lighting model. If you're not a graphics person, don't worry about that. That's kind of the standard way that lighting is done in games. It optionally supports one texture map. It optionally supports fogging, and it optionally supports per-vertex color data. This table on the right shows the different performance implications of changing these options. It's listing the cost in GPU shader instructions, which basically the larger that number, the longer this is going to take to draw. The column on the left shows how much every vertex costs, and the column on the right shows how much every pixel that's drawn to the screen is going to cost. So you can see that drawing with no lighting is quite cheap. Turning on one light, if that light is evaluated per vertex, a little more expensive. Turning on 3 lights, it's considerably more expensive. So we did a hotspot optimization in the shader code for the case where there's just one light. If you don't need all 3 lights, don't turn them all on, and your graphics will render faster. You'll notice there's no entry for just 2 lights. We don't have a special case shader for 2 lights. So if you turn on just 2, it's going to perform the same as if you used all 3, so you might as well use that 3rd one and make it look better. There's also an option for per-pixel lighting. This is not a great choice on the phone. You'll see that pixel cost is very high for that shader. I'll show you what that looks like on the device in a moment. And you can see in the bottom also, turning on a texture map adds a slight overhead. It's not too bad. Turning on fogging is going to slow your vertex shader down by 4 instructions. That's not horrible. Fog is a great effect, and there's times when you need to use it. But you need to be aware also, fog is not free. So don't turn this on except when you actually do need to use it. So I'm going to flip over to an actual phone and show you some of this stuff running on a device. This demo goes through the different 5 effects that are built in. So I'm going to start with Basic Effect. This is a 3D model rendered using Basic Effect. It's pretty high detail. This was created for Xbox 360, but I can render it just fine on the phone at good frame rate. So I have touch controls to zoom in and out. I can zoom way in. You can see there's a lot of triangles in that guy. If I zoom out, let's turn the texture off. That's just the lighting on its own. Turn the texture back on. So at the moment, this is being rendered using the 3 vertex lights shader. If I change that down here to 3 pixel lights, it still performs fine because the tank is quite small. So even though my cost for every pixel has gone way up, switching the shader like this, I'm not drawing very many pixels, so my performance is still fine. If I zoom in, you can probably guess what's going to happen. Now I'm drawing pretty much every pixel on the screen using that very expensive pixel lighting shader. And it's going chunk, chunk, chunk. Not so smooth. Let's fix that by turning lighting off entirely, and it runs at a great frame rate again. And we'll back out to the main menu. So the thing to be aware of there is be careful with that pixel lighting option. It does give you slightly higher quality. And if you have just a little player character that only covers a small part of the screen, go for it. If you turn that on for your background or your main game world, it's going to hurt. Dual Texture Effect, new in Game Studio 4, is an awesome choice for phone graphics. What this does, it takes 2 textures, a base texture and an overlay second texture, each of which has a separate texture coordinate, so you can map them differently onto the model. And it multiplies them together. And it does that with what we call a modulate 2x combine mode. So it's A times B times 2. And what this does, if the second texture is just flat gray, you just get the first texture. If the second texture is darker than gray, the first texture goes darker. If the second texture is brighter than gray, up to white, it makes the original texture brighter. So you can use this for effects like light maps or detail textures. The thing that's great about light maps on the phone is that they let you fake the illusion of really sophisticated, great-looking lighting. But if you look at the shader costs for this guy, you'll see it's very cheap. Just 7 vertex shader instructions and only 6 pixel shader instructions. So the way this works is you can set up your 3D scene, build your world, go into a modeling package like 3D Studio Max or Maya, and they all have functions for creating these light maps. So you set up thousands of lights, as many lights as you want. Use crazy soft shadows, radiosity lighting, all that awesome high-end stuff. Click a button, it'll whir and click for maybe 3-4 hours, and it spits out some great textures. You put the textures on the phone, and the phone hardware doesn't have to do any lighting at all. It just draws the texture. It's all pre-computed. That's really pretty cool. And if you've looked at the keynote demos, the things we've shown running on the phone, most of those are using this effect with light maps in various ways. So I'll show you what this guy looks like. This is not such awesome artwork as we showed in the keynote demo. This is programmer art made by us back at home. So what we have here is a simple little 3D scene with a couple of boxes. I can spin around it. If I turn off the light map, the base 2 textures are totally flat and there's no lighting at all. I'll turn the texture off and turn the light map on. So this is the light map texture that was computed using Maya. And you can see that's providing shadows, and it's providing a couple of tinted glows where the lights are positioned. And when you combine the base texture with the light map, you get the impression of shadows, lighting, all this awesome stuff. But it's crazy cheap, and it runs at a really good frame rate on the phone. So that's a great shader, and you should definitely think about using it. Alpha test effect is going even deeper down the rat hole of cheating. If we want to do things that look more impressive than we actually have the power to do, cheat. Nobody will ever know. So what this guy does, it takes whatever you're drawing and it examines the alpha channel and just throws the pixel away if the alpha is less than a value that you specify. If you're a graphics programmer from a Windows background, you're probably used to hearing that alpha testing is good for performance because it lets you not have to bother rendering pixels that have zero alpha. That's not true on the phone hardware. Alpha blending, just that way where you do translucency, is actually free on this GPU. So you can use that on everything. You can use it with any of these 5 effects, and it won't cost you anything at all. The purpose for alpha testing is if you want to take these things that have alpha channels and put them in a 3D world and have them work with the Z buffer so that objects that are behind them will sort correctly. It's not too expensive. And the thing that's great about this is that you can draw very complicated stuff into a render target and then draw it using alpha test effect. So I'm going to show you a demo of this guy. We have here a lot of that tank model. That is a very high polygon tank model. If I tried to draw that many on the phone, my frame rate would not be awesome. But here, I can spin around them. You can see it looks totally 3D. The tanks in the foreground are covering up the tanks in the background. What I'm doing there is I'm just drawing that tank once into a render target, and then I'm taking copies of that render target and putting them blah, 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 all through the 3D world using alpha test effect. The downside is that you probably notice the tanks all look the same. Well, that's because they are the same. They're all coming from the same render targets. That's because I'm cheating. But it's a great effect for things like a crowd scene. If your game calls for, you're going to get attacked by 1,000 zombies, well, you probably can't draw 1,000 zombies at a great frame rate. But you could draw 5 zombies, and then you could draw copies of them in different places. And mix and match, jumble them up. 5 zombies will give you enough complexity that the user will see, one's got a different hat on to the others. They all look different. But there's way more than you're actually drawing. This can also be a useful effect for games where the camera doesn't change position that much. Things like an RTS game, where you might have a very complicated building that's made of some very detailed, intricate geometry. And drawing this guy is going to take quite a while. But if the camera mostly is just stationary or just kind of pans around, and only quite rarely does it rotate, then you could say, the first time you need to draw that building, draw it into a render target. Then use impostering to draw that render target to your actual scene. And you can draw the characters running around and doing explosions and all your gameplay over the top. And then you only need to bother recreating that render target if the camera rotates. So it's kind of like caching. Skinned effect is for drawing characters that move. That's fairly obvious. The way this works is that you have to write C# code that animates the bones for the skeleton of the character, which runs on the CPU. If you're not familiar with doing that, go to the creators.xna.com website, where we have some samples that show you how to do things like blending between two different animations. Once you have that playback code, you end up with a list of matrices, and you hand these to the skinned effect shader, which plays back the animation entirely on the GPU. It supports up to 72 bones within a character, and it supports either 1, 2, or 4 weights per vertex. And that controls how many different bones can affect a single part of the skin. So with just 1 weight per vertex, you don't get really to flex like that. You just get robot-style animation where arms do that. With 2 bones, 2 weights, you can make more detailed, kind of more fluid-looking skin animations. 4 weights, great looking. But it costs a little more. You can see from that table that 4 bones costs 13 more vertex instructions than if you had just 1. And this shader uses the exact same lighting model as basic effect. So you have the same choices of 1 light is faster than 3 lights, and vertex lighting is faster than pixel lighting. So I'll show you this guy on the device. This is a character model being animated using the skinned effect shader. You can see I can rotate around him in real time. And he's playing back that animation. This guy is using 3 vertex lights and I think 4 bones per vertex. The final shader I'm going to talk about is environment map effect. The way this works, it uses a thing called a cube map, which is a special texture that's made out of 6 textures which form the sides of a cube. So you can imagine that that encases the object that's in the center of it and can describe what its surroundings look like. So this shader looks up a base texture map, and then it also looks up a reflection cube map. This is a great way to make things look shiny and reflect their environment. It's also a great way to fake lighting that looks more complex than it really is. I'll show you this guy in action with a few different options. So this is a photo I took last year, I think, when I was on vacation in Oregon. This UFO thing came down and hovered above the coastline, and it looked exactly like that. So I'll turn the environment mapping off completely first. So that's the model with its base texture. It's not shiny at all. Using the environment map control, not that one, let's get the right one, I can turn up the environment map. So you can see now none of the texture is showing at all. It's just the cube map, and it looks totally reflective, chromium, shiny. That's great if everything in your game is made out of metal or mirrors. Realistic objects tend to be kind of somewhere in between. So for that, you want this control called Fresnel. What Fresnel shading does, it simulates the way light behaves when it hits shiny objects in the real world. So if you have a surface like this and light hits it at that angle, it mostly just bounces off, and you see the color of the surface, not the color of the reflection. But when you have a glancing angle, if light comes at this angle, then it all just reflects straight off the surface, and you tend to see more reflection. You'll see this if you look at a wet road or look at some water. If you get your eye really down low to the surface, you'll see a totally different kind of reflection. So if I turn up the Fresnel control, you can see that in action. Now, when the UFO rotates so that it's facing straight towards the camera, you don't see really any reflection of its surroundings at all. But when it goes like that so that it's edge on and you're seeing its underbelly, it's much shinier just at those angles. The other thing you can do with this shader, apart from making things look shiny and reflective, if you turn up the specular control, that makes it look like it's being surrounded by many, many lights. And what this is doing, it's taking the alpha channel out of that cube map texture and just adding that to the surface. So whatever pattern I draw into that alpha channel is going to look like it's the lights around me. For the one I'm using here, I just drew a load of dots. I just loaded the cube map into Photoshop, and I just chose a little circle tool and went bing, 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 bing. I draw maybe 30 of them. So you can see it has all these little bright highlights, like it's being lit by many, many lights from different directions. I could draw big streaks and different blobs to get all kinds of different lighting effects. So when you're thinking about performance on a phone, it's a pretty nice GPU. It's not an Xbox GPU. If you come from an Xbox background, you probably noticed that Xboxes are fairly large and their power supply is about that big. That wouldn't work in a mobile form factor. So you need to watch performance in a way that you don't on an Xbox. And there's 3 things to balance when you're thinking about this. These 3 things are inextricably linked. If you want one of them to go up, one of the other ones has to go down to make room for that. The 3 factors are, how many pixels are you drawing? How long does it take to draw each one of those pixels? And what frame rate do you want your game to run at? Frame rate is pretty straightforward. The phone runs at 30 hertz. That's the speed of the display. You can render faster than that if you want to, but it's completely pointless because the screen won't keep up and you're just rendering data that's never going to make it to the user. You specify this by setting the game.targetElapsedTime property, like I'm showing there. You can set that to something lower than 30 hertz if you want. There's times when that may make sense. If you have a game that's not super interactive, it's a turn-based thing or an RTS, where you don't need that silky smooth response time, and you want to have time to draw more detailed graphics, you may say, OK, 20 frames a second is fine for this game. Generally, 30 is a good place to be thinking. Pixel cost, there are many things you can do to control. I just took you on a quick tour through the different shaders that are included with Game Studio 4 and showed you how the different options that you set on these shaders affect the pixel cost. I'm not saying don't use the more complex shaders. There are times when that makes sense, but you need to be aware that some are much cheaper than others. If you do things like use dual texture effect for light maps, use the environment map effect to fake specula from many, many different lights, your pixel cost will be quite low. If you use basic effect with per pixel lighting on for everything, it's going to be much higher. The other factor that affects pixel costs is how many times you render to each pixel. If you have a situation where you draw the sky, then you draw a building, then you draw a second building that was in front of the first building, then you draw a tree that was in front of that building, and then you draw a character who's standing in front of the tree. By the end of all of this, you've shaded that pixel 5 times, when only one of those shading results is actually visible. So there are many things you can do to try and avoid that, ranging from the very simple, just do a distance cull. If something is more than a certain distance away, just don't bother to draw it, up to crazy hierarchical visibility systems like BSP trees and spatial partitioning. One very simple thing you can do is just sort all of the objects in your world. Draw the closest ones first, and then the further away ones later. And that will actually enable the GPU to fairly efficiently throw away and not bother shading the more distant objects. A great way you can tell how much overdraw you have in your scene is to build a debug mode into your game. I like to call this X-ray mode. What you do is you change all of your objects to turn off whatever shading they're doing, turn off their textures, turn off lighting, just use like a dark gray color, and turn on additive alpha blending. So every time you draw to a pixel on the screen, it will blend a little bit brighter. And then you can look at the final result, and if it's dark gray, great, you drew that pixel once. If it's white, ouch, you drew that pixel a lot of times. And then you can look at, OK, why did I draw that pixel 10 times? Maybe I can change my artwork or adjust my level layout to not need to do that. The final choice you have control over is how many pixels you want to render. This is a really unique feature to this phone hardware, that you get to control that. On Windows, you generally just have to render to whatever resolution the screen is, and you don't have so much control. The resolution that we're launching with on this phone, 800 by 480, is an awesome resolution for things like browsing the web, displaying text, rendering web pages, using user interfaces that display lots of information. It's a very high resolution. It looks really nice and crisp. But it's a lot of pixels. It's 25% more pixels than the original Xbox console. The GPU is not as powerful as the original Xbox One console. So you need to think that through if you're making an intensive 3D game. You might choose to render at a lower resolution. You don't have to render at full screen res. Some games, particularly simpler games, 2D games, are going to be fine at 800 by 480. But for complex, intensive 3D scenes, you don't have to drop all the way down. Just go down to 600 by 360, and that's only half as many pixels. So you can draw twice as much stuff, or you can run at twice as good a frame rate. The great thing about this scaling is that it's a built-in feature of the hardware. It's not GPU scaling. So the quality is very good, and it doesn't use any GPU time. It's literally free. It's just running in parallel on its own little dedicated bit of silicon. And the scaling quality is very good. So I have a quick little demo that's going to show you this in action. So let's go into this particle system submenu. If you've seen me speak before, you're probably wondering how I've made it this far through the demos without showing any pictures of cats. Well, here they are. This is a simple little 2D particle system using the sprite batch. Wherever I touch the screen, it's going to create cats, and they're going to zoom off. If I want to create a lot of cats, I can turn up this spawn rate control, and it will start automatically creating cats for me. This is running at a great frame rate, even in full 800 by 480 resolution. But if I turn the spawn rate way up, the frame rate starts to suffer because I'm drawing so many cats. I'm actually drawing over the entire screen about 10 times now. And the poor little GPU just can't do that. This is a fairly stupid demo. I don't think an app that just draws loads of cats is going to be hugely successful. But imagine this was explosions in a space shoot-'em-up game, and you wanted crazy intensive, I just blew up the Death Star, and I want bloom particles everywhere. This is the kind of thing you might very well want to do in a game. So OK, I want that many cats. It's running too slow. I can just change the resolution. Now I'm running in 360 by 600 mode, and you can see it's way smoother. And if I change it again, 240 by 400, that's rendering quarter the number of pixels that it originally was. It's totally smooth. It looks great. The text is a little blurrier, but not bad. So that's really the trade-off you get to make. Do you want super crisp, high-resolution pixels with less performance? Or shrink it down, sacrifice a little bit of crispness for more detail and more performance? I know when I say the text is slightly blurrier through this wolf thing, you probably can't see that in detail. If you want to come up afterwards, I can show you this running on the actual device so you can get a sense of just how smooth it really is. There aren't many gotchas in the Game Studio API. We tried very hard to build it so that there weren't little funny corner cases that would trip people up. But there's just a couple of things that you should know. If you're working with render targets, there is a render target usage selector with 2 values. Don't ever, ever, ever use preserve contents for anything. It will destroy performance. Discard contents mode is the default, so just don't do anything and you're fine. Just don't change this away from the default if you want your game to run fast. A general pattern with any graphics objects is you should create these once at startup and reuse them. Don't create them every time you want to draw something. So if you see code that does something like setting device.blendState equals, I'm going to make a whole new blend state object from scratch and fill it in, that's a problem, because every time that runs, every frame, it's going to make a new instance of this type. The graphics driver and the graphics runtime is much happier if it can just reuse the same object that it's already figured out the hardware back-end command buffers for. So you should create your blend state once at startup, store it in a static. Then every time you want to draw something, you can just reuse that. Same thing goes for textures, vertex buffers, index buffers, effects. If you're writing code that generates new vertex data on the fly while the game is running, be careful about using the vertex buffer setData API. SetData is a good way to set your geometry up once while you're loading, but you shouldn't be calling this every frame. That can cause stalls in the pipeline and prevent the CPU and the GPU from running in parallel. Instead, use the drawUserPrimitives API, where you just pass it a C# array containing your vertices. The time when you may not want to do that is if you're doing something like generating some vertices that you're going to draw, and then draw again the next frame, and then again the third frame, and then just change them on the 4th frame. You might not want to have to pass that array every time. In that case, you should use the dynamic vertex buffer type. Use the setData options no overwrite flag and the discard flag to indicate how you want the GPU to handle this stuff. To summarize this, I've thrown a lot of information at you. The thing about performance is it really comes from knowledge, and the more knowledge you have, the better performant code you know how to write. So I've just thrown out a bunch of knowledge. If you had to pick which bits of this to pay attention to and remember, I think probably the most important things for anyone in .NET who wants to write fast code is really understand the difference between value types and reference types. Don't just kind of skim over it. You can make things work without understanding the difference in detail. To get things to run fast consistently, you do need to understand that. Understand how the garbage collector works so that you know what to do if it turns out to cause problems for your game. It's totally possible to optimize code so that the garbage collector is not a problem ever if you understand what's going on. Understand the C# compiler. Know what it's doing. Use Reflector to look at what it does to your code. And understand the different graphical effects that we have to choose from. We've given you a palette of 5 of these. Each of them has about 10 different knobs to adjust. And where you set those knobs will affect how fast they run. 2 main takeaways. If you don't have these guys already, get CLR Profiler and .NET Reflector. They're awesome tools. And think about display resolution. You get to pick any resolution you like. There's not going to be one resolution that's correct for all games. That's your trade-off to make. It's up to you to decide what the right trade-off is for your game. Experiment. Figure it out. I'm going to take some questions now. If you'd like to come up to the microphone and ask away.
Hey, I was just wondering, what's the refresh rate on the phone?
30 hertz.
30? Thanks.
Yes.
I'm a little, want a little more detail on obfuscation and the access that users have to stuff that's on the phone. As we all know, non-obfuscated code, you put the reflector to it or whatever, and you can get the source code back. They said in an earlier session that they wouldn't be able to get anything off the phone. Well, how do they get their photos? How do they get other stuff like that? Could you just address that
Sure.
a little? Thanks.
So there's a couple of levels of protection there. It's not, end users don't have a direct way to copy application code back off of the phone onto a PC to reverse engineer. I'm not going to say that it's impossible. Sufficiently determined hackers can get anything from anywhere, no matter how hard we try to protect it. But there are protections in place so that this isn't trivial. A couple of extra levels of protection you can look into if you're concerned about this is there are .NET obfuscation tools that you can use to make your assemblies harder to reverse engineer. And the final protection you have, which I actually think is by far the most valuable, is the legal system. There's a real double-edged sword to .NET code being so easy to reverse engineer that yes, someone can grab your assembly and look how it works in Reflector, but you can also grab their assemblies and see if they put your code in them. That actually gives you a fairly strong... Is any company really going to ship with code that they stole from somebody else that's very easily visible to everyone and provable to be stolen?
I had a couple of questions, actually.
Sure.
Number one, do we have access, or are we going to have access to programmable shading?
Programmable shaders are obviously an interesting feature. That's something we would love to get at someday. We don't have any specific plans at this point to announce. For this first release, we really focused on making something that was going to be robust and that was going to give good performance and that we could give the right compatibility guarantees and make sure it was properly future-proofed.
Okay. And also, any horizons on getting PIX or something like that to work?
Nothing I can comment on at this time, sorry. Any more questions? Well, thank you very much.